Let me welcome you to this lecture. We will now discuss the chemistry of group 12 organometallic compounds, and during this lecture we will focus on organozinc compounds. Now, organozinc compounds or preparation of organic zinc compounds again follows uh, conventional methods for preparation of main group organometallic compounds. One can start with ethyl iodide, and its reaction with zinc will give us, which generally exist in association in aggregated form, not as monomer, depending upon the condition. And when this compound is heated, essentially it undergoes this proportionation reaction, where to give us nitrile zinc and zinc iodide. So that is one of the methods for preparation of organozinc compound. The second method is one can start with zinc and add organomercury reagents, and this will again give us R2Zn, and mercury, metallic mercury is going to come out of this. Third conventional method is to start with organoalkyl reagents, and in this case one can use uh, either alkyl lithium, or in fact one can also use Grignard's reagent, and this will also give us R2Zn, and depending upon whether you have used RLI or RNGX, the byproduct is going to be LiCl or MZXCl, any one of these. Then there is another method. One can use also alkyl aluminium reagents for preparation of organoaluminium reagents for preparation of organozinc compounds, and one can start with zinc acetate and then R3Al. Upon reaction with organoaluminium reagents, once again one can get R2Zn, and aluminium acetate will essentially be the byproduct in this reaction. So these are some conventional methods for preparation of organozinc compounds, and many of these organozinc compounds serve as important reagents in organic chemistry, and we will of course learn about these reactions where organozinc reagents are used. So unlike group 2 organometallic compounds like organoberyllium compounds, or organolithium compounds, which form aggregates in both solid as well as in solution phase, the organozinc compounds are quite electron rich as compared to these organolithium or organoberyllium compounds, and that is why these organozinc compounds, that is R2Zn, exist as monomer, not as aggregates, unlike the organolithium or organoberyllium compounds that we have learned, which exist as aggregates. Now, because of these reasons, monomer, the intermolecular forces of interaction between organozinc molecules are essentially weaker, and that is why these compounds, organozinc compounds, have generally low melting point and boiling point. So their melting point and boiling point are going to be much less as compared to what you see for organolithium or organoberyllium compounds, which we have discussed earlier. And the compounds are essentially, the structure of these compounds are linear in this way, where the R Zn R angle is close to 180 degree, and because their electron reach, again these compounds do not tend to form this sort of breaching species or aggregates. They do not tend to form aggregates by forming this sort of two electron, three centered bridging bonds by using the organic substituents as the bridges here, and that is how they differ from these organolithium and organoberyllium compounds. But although these sort of bridges or bridging compounds or bridges formed by organic substituents are not favored, but these hydride bridge compounds are essentially formed much readily in case of these organozinc compounds, and one can see examples of such. So if we start with say diethyl zinc over here and then do reaction with a zinc hydride to form a organozinc hydride compound. Now this can form a hydride bridge species, and this leads to formation of essentially aggregates or hydride bridge aggregates in this way. So this reaction is done in presence of a Lewis base pyridine. So then you will have zinc will have both pyridine and the ethyl groups will be attached to the zinc centers in this way. So at this again, this ZnH Zn linkage, these are all two electron, three center linkages, the way we see similar hydride bridges in case of boranes. Although they are not as electron, these organozinc compounds are not as electron deficient as these organolithium or organoberyllium compounds, because there are 10 d electrons in these compounds, but there is some electron deficiency, and that is why other sigma donor ligands can bind to these organozinc compounds. And examples, say for example, we know that this is linear, essentially the organozinc compounds, but the moment a sigma donor ligand comes in attack, the linearity is, it deviates from linearity, and say this is OR O Me2, that is an ether, this is a sigma donor again, and we see the other sigma donors, say for example the DMEDA, which is a sigma donor solvent. It can also come and bind with these organozinc compounds in this way. And if you choose the right sigma donor ligand here, it can also lead to formation of aggregates. So for example, if we use halides or alkoxides as the sigma donor ligand here, then one can get aggregated organozinc compounds. So for example, one can get aggregated structures like this here. So these X can be here either halide or acetic oxide. So let's write it as halide. So this sort of dimeric structure can be formed because of the sigma donor ligands that are present here. And again, dimeric structures are also possible. as well as tetrameric heterocubin-like structures are also formed. So we have the this is going to be only one R group, not two R groups yet. In case of these as well, only one R is going to be retained. So for these as well, we'll have only one of these organo group is going to be attached to the zinc center, and these sort of aggregated moieties are formed when the right kind of sigma donor ligands are attached to the organozinc compounds. That is halides or alkoxides. Now, another important or another interesting organozinc compound is this methyl cyclopentadienyl zinc, that is CpMeZn, which is an 18 valence electron species. And the structure of this compound in gas phase, it has a monomeric structure. So what we see is in gas phase, it is in gas phase. It has monomeric structure, and it is again a compound is linear in nature, the geometry, and we see that the one electron is dominated by this methyl group. Zinc, there are 12 electrons, valence electrons in zinc, and then 5 electrons are dominated by this Cp ligand. So that is how it's a 18 valence electron species. But in the solid state, the structure is different. It has a polymeric structure, where the Cp ligand essentially breach the metal centers. So that is how the Cp ligands breach the metal centers, the zinc centers in this polymeric one-dimensional chain structure in the solid state of this compound. So another interesting compound, organozinc compound, is Cp star 2 Zn. So it's a metallocene compound with sandwich structure, and for this particular compound, one of the Cp ligand is in eta 1 coordination mode, while the other Cp ligand is eta 5 coordination mode, and only then we can have an 18 valence electron species here. And now if you look at the structure of this compound in the gas phase, so there are methyl groups are there. Which is Cp star. So this is how the structure is in the gas phase, and the distance, again, if you want to look at the bond distances, distance from the metal center to the basal plane of these Cp ligands here, this particular bond distance is quite longer. Here this is around 190 picometer, and the other one is 100 this is 208 picometer, while this is 193 picometer. The one which is eta 5 coordination mode, it has shorter distance to the metal center, while the ligand CP ligand with eta 1 coordination mode, it has longer distance from the metal to the basal plane of the CP ligand. And now in the if one records the proton NMR spectra of this compound, what one finds is that there is only one type of signal for the hydrogen atoms are obtained, and both the CP ligands essentially appear equivalent in the NMR spectra. The reason is because the metals or the CP ligands here just changes the hapticity at a very faster at a rate which is faster than the NMR time scale, or there is a heptatropic because hapticity of this ligand is essentially changed, and this change in the hapticity of this ligand is faster than the NMR time scale, and that is why we obtain only one signal in the NMR proton NMR spectra of this particular compound. That is a very interesting aspect of this or the interesting fluxonal behavior of this sort of compounds. Now, if we look at the reactivity of these organozinc compounds, what we find is that they are much less reactive as compared to organolithium or organomagnesium reagents, and that is why one uses these organozinc compounds in reactions where there are milder reaction conditions as well as non-basic medium is required. So we have already seen examples where such organozinc compounds are used for preparation of metal alkyl compounds, which where one substitutes less number of halide ligands from the metal center. Or so if we take diethyl zinc and do reaction of it NaCl5, we can now control the reaction, unlike what we can do in case of when we use lithium or organolithium or organomagnesium reagents. Herein one can substitute only two of the Cl ligands to get diethyl niobium trichloride as the product in this case. So the byproduct is going to be ZnCl2. So that is how one can use organozinc reagents in reactions where, or organometallic transmethylation reactions where one needs to use milder reaction conditions. So another important application of this organozinc compound is in the Reformatsky reaction. You may have already learned the Reformatsky reaction, where an organozinc intermediate is essentially formed. In the Reformatsky reaction, we know a alpha bromo ester is essentially transformed into a beta hydroxy ester. So one starts with an alpha bromo ester and does reactions with once reaction with zinc to undergo oxidative addition to the zinc center, and a dimeric intermediate is essentially formed. This sort of dimeric intermediate is formed. So reaction is done in donor solvent like THF. And in this dimeric intermediate, we see that these these alpha bromo esters have essentially, now it has become this CH2 groups. They have become they are nucleophilic. They have acquired nucleophilic character now, and that is why they can undergo reaction, nucleophilic addition reaction to ketones especially, and that is how it will come and now react with the carbon atom over here to give us an after hydrolysis, that is after hydrolysis of the product or reaction mixture, we will end up with a beta hydroxy ester as the product. So what we see is that a dinuclear organozinc intermediate is formed in the reformatsky reaction, and formation of this intermediate is important for completion of this reformatsky reaction. Another important application of organozinc compounds are as organozinc carbenoids. So one reaction where these organozinc carbenoids are used is the Simmons-Smith reaction, where a organozinc carbenoid essentially is added to a olefin. So the preparation of preparation of these organozinc carbenoids, one can take this by methyl iodide, and its reaction with zinc will give us a organozinc carbenoid, that is ICH2ZnI, which is a organozinc carbenoid. Because CH2 group is there, that is why we call it the carbenoid. Now this CH2 group can be added to a double bond here. So this it can be added to this double bond, and this will lead to formation of a spirocyclic compound. And this way it will be formed. So if you look at the mechanism of this reaction proceeds through a concerted mechanism where, so if I take the double bond and add this, so a concerted reaction is going to take place wherein the CH2 is going to be added to this double bond. And the cyclopropane is essentially formed in this way, and ZnI2 comes out as the product. So this is how spirocyclic compounds, or even cyclopropane derivatives, can be prepared by using organozinc carbenoids and with their reaction with olefins. Such organozinc carbenoids are also used for ring expansion of aromatic compounds actually. So CH2 here and ZnET. Now this particular carbenoid, this is now a carbenoid we have here. This can be added to aromatic rings like benzene here, and then the rings are essentially, aromatic rings are going to get expanded. This sort of, now we have a cycloheptatriene is formed by through reaction of this benzene with this organozinc carbenoid reagent, and we have already learned that such ligands are very important in organometallic chemistry, and this is how one can prepare such cycloheptadiene or such conjugated olefins, cyclic olefins, by using this organozinc carbenoid as the reagent. So this brings us to the end of this lecture. What we have learned during this lecture is about organozinc compounds. We have seen how one can prepare these organozinc compounds. Also, we have looked at the structure of these organozinc compounds. We have learned that they exist as monomers in both solid as well as in solution or in gas phase because of the electron-rich nature of these compounds as compared to analogous group 1 or group 2 organometallic compounds. So then we have looked at the also how one can obtain aggregates, or how sigma donor ligands, when we use sigma donor ligands of the right kind, one can end up with aggregates of these organozinc compounds. So when we use halide as the sigma donor, or alkoxides, sterically less bulky alkoxides as the sigma donor ligands, we can end up with dimeric, trimeric as well as tetrameric aggregates of these organozinc compounds. Then we looked at two important organozinc compounds containing cyclopentadienyl ligand. One is the CP methyl zinc, which exists as monomer in gas phase but exists as a polymer, CP polymer, where the CP ligand essentially breaches the metal centers. And then we have also looked at another sandwich compound of this zinc, where actually slip sandwich compound, not exactly sandwich, because one of the CP ligand in this CP star to zinc essentially uses eta 1 coordination mode, while the other CP ligand uses eta 5 coordination mode. Then we looked at the reactivity of these organozinc compounds, and we have learned that these reagents can serve as, these organozinc reagents can serve as milder counterpart to these group 1 or group 2 organometallic compounds, and they can be used in reactions where one needs to partially substitute the halide ligands from the metal center, as well as one in cases where milder reaction conditions and non-basic mediums are required. Then we learned about the application, or the how organozinc compounds serve as intermediates in important reactions like reformatory reaction, where a dimeric organozinc species is formed as the intermediate, and which allows us to form this beta hydroxy esters starting from alpha bromo esters. So then we looked at the application of organozinc carbenoids in organic chemistry, and we have seen that in case of the Simon-Schmidt reaction, we discussed the organozinc carbenoids essentially allow us to form cyclopropane derivatives, as well as different spirocyclic compounds. Then we learned about another important application of these organozinc carbenoids, where one can use these organozinc carbenoids for ring expansion of these aromatic compounds, which essentially gives us cyclic conjugated ligands, which are important in organometallic chemistry. So let me conclude this lecture with this, and I thank you very much for being with me during this lecture.